Before we evolve to driverless electric vehicles and engines using free valve technology, let's take a look at the tried and trusted four-stroke engine. Its job is to convert the chemical energy from a hydrocarbon-based fuel to mechanical energy that can be used to drive a gearbox. Whether we're looking at a spark or compression ignition internal combustion engine, we need to understand a little bit about thermodynamics. This is a branch of physics that deals with the relationship between heat, chemical and mechanical energy. The basic principle of operation for any internal combustion engine is to use the heat energy from burning a hydrocarbon fuel to create large amounts of heat. Heat energy can be used to create pressure, which can then be used to exert force upon an object. The four-stroke engine uses pistons in an enclosed cylinder to transfer the force to a crankshaft, which in turn changes the downward movement of the piston into a rotational motion. It's this rotary action that creates the torque we need to turn our gearbox to move the car. So, let's take a look at a single-cylinder four-stroke cycle. Our engine is constructed into an upper and lower assembly, with both used for creating the heat and pressure required by an internal combustion engine. The upper assembly, or cylinder head and valve train, controls the flow of fuel and air into the combustion chamber. The cylinder head is attached to the lower engine assembly and forms a combustion chamber and cylinder for the piston to operate in. Our engine crankshaft is attached to the camshaft via chains, gears or a belt, and its rotation is used to operate the intake and exhaust valves. The upper and lower engine assembly differs between a spark and compression ignition engine, as the latter requires much higher pressures for energy conversion, so it's constructed with this in mind. The four separate strokes that make up a complete cycle take place over 2 complete crankshaft revolutions. The camshaft is geared to turn at half the crank speed, so for an engine cycle to complete, the camshaft will rotate only once. Traditionally, on a spark ignition engine, the intake stroke allowed an air-fuel mixture to enter the cylinder. From top dead centre, rotation of the crankshaft pulls the piston down the cylinder bore, while at the same time the intake valve is opened by the camshaft. Since atmospheric pressure is much higher than that of the void left by the piston, air is pushed into the cylinder to fill this space. On a carburetted engine, the airflow will mix with a metered quantity of fuel before continuing through the manifold, past the intake valve and into the cylinder. An indirect injected gasoline engine has its fuel injected onto the back of the intake valve, where it mixes with the incoming air before entering the cylinder. While a compression ignition or gasoline direct injected engine will only see air enter on the intake stroke. Near bottom dead centre, the intake valve is closed by the camshaft, trapping the charge within the cylinder. Further rotation of the crankshaft begins to push the piston back up the cylinder, compressing the charge to a high value. The higher the compression, the more energy can be extracted from a given amount of air-fuel mixture. This is the most thermally efficient way to convert the stored chemical energy. Approaching top dead centre on a GDI and compression ignition engine, the fuel is injected. It's done at this point because this is where cylinder pressures are reaching their highest value. Just before top dead centre, ignition of the air-fuel charge takes place, in the case of a gasoline engine through the use of a spark plug, or from self-ignition in a diesel engine. Momentum of the crankshaft carries the piston through top dead centre and into the power or expansion stroke. The air-fuel charge expands after it ignites, releasing large amounts of energy in the form of heat and combustion gases. Pressures rise rapidly within the cylinder, causing the piston to be pushed down the bore with a considerable force. This force is what drives the crankshaft, creating the torque required for vehicle movement. Near the bottom of the power stroke, the expanding gases have cooled slightly and lost most of their energy. So it's at this point the exhaust valve is opened. Momentum of the crankshaft and flywheel drive the piston back up the cylinder bore, forcing the spent gases past the exhaust valve and into the exhaust manifold. As the piston nears top dead centre, the intake valve is opened, allowing a fresh charge to enter the cylinder while waste gases are still exiting. A single cylinder engine's torque output can be improved upon by simply adding more cylinders. Each cylinder in the engine is timed, so its firing pulses take place in a controlled and balanced way. An inline 4-cylinder engine using a flat plane crankshaft has cylinders 1 and 4 acting on the same axis, separated by 180 degrees from cylinders 2 and 3. This means that while cylinder 1 is on its power stroke, cylinder 3 is on its compression stroke. Cylinder 4 is on its intake, and cylinder 2 is on its exhaust. No cylinder is ever on the same stroke at the same time, resulting in a reasonably balanced engine. We can see a 4-cylinder inline engine has a firing order of 1, 3, 4, 2. 4-cylinder box engines, like the Subaru, use a flat plane crank to achieve a firing order of 1, 3, 2, 4, due to their horizontally opposed design. When operating, the cylinders on one bank fire sequentially and are then followed by the opposite side. This firing order, coupled with separate exhaust manifolds, is what gives them their unique sound. A 6-cylinder inline engine has opposing cylinder pairs constructed with 120 degrees of journal separation. With more firing pulses per crankshaft rotation, an inline 6-cylinder engine is remarkably well balanced. Most V6 and V8 engines use a cross-plane crankshaft, where the journals are spaced evenly around the crank's axis. 8-cylinder engines in a V configuration have a firing pulse every 90 degrees of crankshaft angle. This makes for a very linear power delivery with low engine vibrations. An engine's capacity can be calculated using some simple mathematics. We can use the engine's bore and stroke to work out the swept volume of a cylinder. This is the swept volume for one cylinder. So the total displacement for this engine is 584 cc's. An engine's compression ratio relates to how much the air-fuel charge is compressed into the combustion chamber. This can be calculated by using the engine's swept volume and clearance volume. The clearance volume of an engine is the total of any area above the piston when the crankshaft is at top dead centre on compression stroke. This includes piston dishes and the cylinder head gasket and combustion area. We all love engines and the new technology that surrounds them, but knowledge of these basic principles must be appreciated before we begin to understand any modern 4-stroke system. Thanks for watching.